Good morning, students. Welcome back to our algorithm class. We have completed 3 units of our syllabus. We are going to proceed into the next unit, dynamic programming. This is Professor Magulan. I'm going to discuss about this dynamic programming in this class. As you know, we are discussing about various problem solving strategies. In the unit 1, we discussed generally about what is an algorithm, what are the characteristics of an algorithm, how to devise an algorithm, and what is a randomized algorithm, how to analyze the efficiency of an algorithm, complexity of an algorithm, and everything has been discussed in the unit 1. In the unit 2, we discussed about divide and conquer method. That is one of the problem solving strategy. There we found out that problems of recursive in nature can be solved using this dynamic divide and conquer method. And we solved many problems using that dynamic programming method like merge sorting, binary searching, finding the maximum and the minimum, like that. We solved many problems using that divide and conquer method. Then we discussed about yet another problem solving strategy, greedy method, wherein problems whose solution can be arrived using a sequence of decisions. Series of decisions can be attempted using the greedy method. There also we solved some example problems like knapsack problem, then optimal storage on of programs on your tape. Then many such examples we have considered. Now we are going on to yet another problem solving strategy, dynamic programming. This dynamic programming. So you should know what is the basics behind this uh, dynamic programming. In dynamic programming also we can solve problems in stages. In stage 1 we are taking some decision, and based on the decision we have taken in the stage 1 we proceed to stage 2. There also we take some decision. Like this, a series of decisions are taken in the dynamic programming problems. Okay, then ultimately we find. Now, in the greedy method also we employed the same technique. There also we used the series of decisions. Then in what way this dynamic programming differs from uh, greedy method? See, in the dynamic programming, we get the optimal solution in whatever from whatever the decision we have taken in the stage 1. Okay, supposing we have taken some decision, wrong decision in stage 1, then we proceed to decisions in stage 2, 3, 4, like that. Then from what uh, what is the maximum that we can get from stage 2, stage 3, stage 4, like that. Okay, even if there is a error in decision error in stage 1. Okay, so it will try to optimize the solution even if there is a error in the stage 1. Like that, if there is a error in stage 2, then it will try to optimize the solution from the next decisions onwards, like that. Okay, so whatever be the initial decisions, the remaining decisions will contribute to optimize the solution. That is the idea behind this dynamic programming. Whereas in greedy method, it is not like that. We follow on some strategy, we make some decision, then based on that we get the optimal solution. Okay, so I can say that dynamic programming will use some kind of damage control mechanism. Okay, so that is many a time useful in our day-to-day life. Okay, now here you should know something about principle of optimality. Principle of optimality. Principle of optimality. An optimal sequence of decisions has the property that whatever the initial state and decisions are, the remaining decisions must constitute an optimal decision sequence with regard to the state resulting from the first decision. That is the definition of this principle of optimality. Now let us explain this. An optimal sequence of decision has the property that whatever the initial state and decision are, the remaining decisions must constitute an optimal decision. With regard to the state resulting from the first decision. So look at this definition. An optimal sequence of decision has the property that whatever the initial state and decisions are, that means if a decision has been taken wrong initially, then the remaining decisions must constitute an optimal sequence of optimal decision sequence with regard to the state resulting from the first decision. Simply saying, some error has been taken in the first decision, then the remaining decisions should try to get the best solution to the problem. Then it's not only with the first decision. If some decisions are taken wrongly in any stage of the problem solving, then the remaining decisions should constitute an optimal solution. Okay, from the damage incurred in a particular stage. That is this principle of optimality. Again, I tell you, an optimal sequence of decision has the property that whatever the initial state and the decisions are, the remaining decisions must constitute an optimal sequence with regard to the state resulting from the first decision. So This is one of this problem solving strategy. Here, uh, we are going to solve some example problems for your understanding. Okay, some of the problems we are going to solve are multi-stage problem, traveling salesman problem, single source shortest path problem, string editing. Like this, we are going to solve some of the example problems based on the dynamic programming problem solving strategy. First, we start with the multi-stage graph problem. Multi-stage graph problem. Now, for your understanding, I bring up one picture of multi-stage graph that will explain you what is this actual problem is. Now, look at this problem. It's a multi-stage graph. Now, this graph is made up of various vertices and various edges. So it is an edge, it is an edge, it is an edge from 1 to 4, it's an edge from 1 to 5, like this. But you see how the vertices are arranged. The vertices are arranged in various stages. This is stage 1, then vertex 2, 3, 4, 5. They are all in the stage 2. Then 6, 7, 8, they are all in the stage 3. 9, 10, 11, they are all in the stage 4. Then vertex 12, it is in the stage 5. So these vertices of this graph are divided into 5 stages. 5 stages. And also you notice every edge. An edge is always from one stage to the next stage. For example, you take this edge. This edge is from stage 1 to stage 2. This edge is from stage 1 to stage 2. Now you take this edge 7 to 10. So this edge is from stage 3 to stage 4. Okay. So an edge will go from one stage to the next stage only. Okay. Then what is the cost? Cost of this edge is the weight value given to that edge. So the cost of this edge is number 4, value 4. Cost of this edge 9 to 12 is 4. Cost of the edge from 11 to 12 is 5. Cost of the edge from 5 to 8 is this 8. Like this, every edge is given a value. That is the cost of this edge. Okay. Now, from stage 1, we have to reach to the stage 5. That is our aim. Okay. Then from stage 1, from where we can go, from which vertex of the stage 2 we should go. Okay, my aim is to go from vertex 1 to vertex 12. Okay, but to go from vertex 1 to vertex 12, I should pass from stage 1 to any other vertex in the stage 2. Okay, so from 1, should I go to the vertex 2 or vertex 3 or vertex 4 and vertex 5? So I have to take a decision. I have to take a decision in this stage. In this stage. So uh, I might, so supposing I take the vertex 2, I am from going from here, I am going to vertex 2 means then one decision has been taken. Then from this vertex, okay, which vertex to go? 6, 7, 8. Okay, there is a decision to be made from this stage to this stage. Okay, should I go from vertex 2 to 6? Should I go from vertex 2 to 7? Should I go from vertex 2 to 8? Okay, supposing I go from vertex 2 to 7, so your decision has been taken. So one decision was taken here, another decision was taken here. Now from here I go to here. Now, vertex 7 is connected to vertex 9 and vertex 10 only. Vertex 9 and vertex 7. It is not connected to vertex 11. Okay, so your decision should be taken here whether to go from 7 to 9 or 7 to 10. Another yeah, decision has to be taken here. Supposing I take the decision of going from 7 to 10, then from 10, you don't have to take any decision because there is only one edge, one vertex to which you can go from 10. So, how many decisions you are taking? Here you are taking one decision, from here to here one, from here to here one, two, then here to one, three. Okay, so three decisions were taken to reach from vertex 1 to vertex 12. So what does it means? Supposing a multi-stage graph is made up of k stage, k number of stages, then number of decisions to be taken to go from the first vertex to the last vertex is k minus 2. What is that? K minus 2. Here, yeah, how, stage 1, stage 2, stage 3, stage 4, stage 5. 5 stages are here. So 5 minus 2 is equal to 3. Decisions are taken. Like that, if a graph is made up of 10 stages, then to go from the first vertex to the last vertex, you need 10 minus 2 is equal to 8 decisions has to be taken. So that is the basic idea behind this multi-stage graph. Now, what is the problem here? The problem is to find the minimum cost path from the first vertex to the last vertex. That is to find the minimum cost of path from a vertex in the stage 1 to the vertex in the stage k, to the vertex in stage k. Okay, minimum cost path. Now, in this example, for your understanding, these dotted edges are the decisions taken path. Decisions taken path from here to here, here to here, here to here, here to here. So, this dotted path gives me the least path, gives me the minimum cost path. That is the idea. That is the aim behind this multi-stage graph problem. Okay, so I have explained you what is this graph problem is. Now I explain this. Here E comma E is a graph with k stages. With k stages. Okay. Then for an edge, an edge I comma j, for an edge I comma j, I belong to I belong to I belong to stage VI, and J belong to stage V VI plus 1. Stage J belonging to VI. What does it mean? for every edge, okay, for every edge I comma j, here I is this one, j is this one, so I will belong to one stage, j will belong to the next stage. You take this one 8 to 11, this edge, so this 8 belongs to to stage 3 and 11 belongs to stage 4. That is what I mean. Okay. Then number of vertices, uh, number of vertices in stage V1, in stage V1 equal to 1, and stage Vk equal to 1. Vk is equal to, okay, see in this graph, this is stage 1, stage 2, stage 3, stage 4, stage 5. Number of vertices in stage 1 is 1, vertex 1. How many vertices are here? Here. How many vertices are in stage 4? 1, 2, 3, 4. How many vertices are in stage 3? 1, 2, 3. How many vertices are in stage 4? 1, 2, 3. How many vertices are in stage 5? 1. Okay, this is final stage. So the number of vertices in the stage V1 is 1. Number of vertices in final stage Vk is equal to 1. Okay. Uh, so still I can elaborate this. G comma V comma is a edge with the k stages. V1 comma V2 comma V3 dot 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 Vk. I can say like this: V1, V2, V3, Vk. Then the problem is to find the cost, minimum cost path from. I call it as source vertex. This is S means source, and this 12 is sink. Source is 1, sink is 12. So aim is to find the minimum cost path. Is to find minimum cost path from source in V1 to sink vertex, from source vertex in V1 to vertex in Vk, sinks vertex in Vk. That is this multi-stage graph problem. Okay, so we have to find such a minimum cost path. Okay, we take this example problem itself. Okay, now how we are going to solve this problem? Okay, we take the very same problem itself. Okay, to solve this problem, we have to generate one formula. So the formula is this one. we devise one recurrence relation. So the problem is solved using the recurrence relation. Cost of I comma j equal to minimum of uh, cost of j comma l plus cost of I plus 1 comma l, where where L belonging to Vi plus 1 and J comma L belonging to E. What is this E? Set of edges. And what is this V? Stage number. What is this? See, I want you to give a greater deal of attention to this particular relation. Unless you understand this relation, you cannot solve this problem. Now, what is this? What does this relation says? Cost of I comma j. The cost from the vertex I to vertex j is nothing but minimum of the cost of j. See here, I means the stage number, j means a particular vertex in that particular stage, particular vertex in the stage I. Again, I tell you, I means the stage number, J means a particular vertex in the stage I. So minimum of J comma L means is a minimum of cost of J comma L, that is from the vertex J in the stage I to L. Where does this L belongs? L belongs to the next stage Vi plus 1. Okay, for your understanding, let us take J is in the stage Vi means then L should be in the stage Vi plus 1. Vi, J is in Vi means L should be in Vi plus 1. Okay, I will come back to this example. Okay, see, cost of 1 comma 1. Cost of 1 comma 1. That cost of 1 comma 1. What does it mean? Cost of 1 comma 1. This 1 means stage number, this 1 means vertex number. Okay, what is the cost of this vertex is from here you go to equal to minimum of C of J comma L. What is this J? J value is this 1 comma then L belonging to the next stage. So this is stage number. What is the next stage? But stage 1 to stage 2. L belonging to the next stage. Okay. So L, any of these vertex in the next stage, 2, 3, 4, 5. So minimum cost of 1 comma from vertex 1, you can go to here. Okay. So 2 plus cost of uh, cost of I plus 1. Here my I value is equal to here my yeah, here my I value is equal to 1. So cost of I plus 1 2 comma the value is equal to 2. L value is equal to 2. Okay. Then this I should do it for every vertex in the next stage. How many vertices? There are 4 vertices are here. So next comma cost of 1 comma 3. Cost of stage 1 to the stage 3. Cost of 1 comma 3 plus uh, cost of uh, 2 comma 3. Cost of 2 comma 3. comma, C of C of 1 comma 4 plus cost of 2 comma 4, cost of 2 comma 4. Then yeah, one more vertex is there, comma C of 1 comma 5 plus cost of 2 comma 5, cost of 2 comma 5. See, try to understand this particular expression. Okay, with this, the minimum cost path from vertex 1 in the stage 1 is nothing but the minimum of cost value from vertex 1 to 2 plus cost from 2 to 12. Then cost value from 1 to 3, that is in the previous case, this is 9. 9 plus cost value from 2 to 12. Then 7 plus cost value from 3 to 12. 3 plus cost value from 4 to 12. 2 plus cost value from 5 to 12. Among this, which is minimum? And that is the minimum cost path from 1 to 12. Now, to find minimum cost value from 2 to 12, okay, I have to take one decision. So then it will be 2 to 4. 4 plus minimum cost value from 6 to 12. Then 2 plus minimum cost value from 7 to 12. Then 1, 2 to 8, 1. 1 plus minimum cost value from 8 to 12. Like this. Uh, that's how we should do it. So cost of 1 comma 1 is nothing but cost value from um, minimum cost value from cost of 1 comma 1 is nothing but yeah, uh, from stage 1 to the next vertex in uh, yeah, here cost of I comma j is minimum, cost of j comma l plus cost of I plus 1 comma l. So cost of 1 comma 1 is equal, I is equal to 1, j is equal to 1, minimum of c of j is equal to 1, 1 comma 2, 1 comma 2, 2. Okay, from vertex 1 to the vertex 2, then vertex 1 to vertex 3, vertex 1 to vertex 4, vertex 1 to vertex 5. Then cost from vertex 2 in stage 2, then vertex 3 in stage 2, vertex 4 in stage 2, vertex 5 in stage 2. We have to find all these values. See, okay, we have to find all these values. It becomes so minimum of minimum of, what is the cost value from 1 to 2? 1 to 2 is 9. So it is 9 plus cost of 2 comma 2 comma, what is the cost value from C of 1 comma 3? 1 2 3 7. 7 plus cost of 2 comma 3 comma 1 to 4 3. 3 plus cost of 2 comma 4 comma 1 comma 5, C of 1 comma 5 2. 2 plus cost of 2 comma 5. 2 comma 5. So I have to find this cost of 2 comma 2. What is cost of 2 comma 3? Cost of 2 comma 4. Cost of 2 comma 5. And put them all these in this expression. Compute this expression. Compute this expression. Compute this expression. Compute this expression. You will get some value for each of these expression. Then among those values, which is minimum, and that is my minimum cost path from vertex 1 in the stage 1 to the vertex 12 in the stage k. That is the problem that we have to do it. Time is getting up. We will see those things in the coming class. Okay. So I gave you a brief idea about what is this multi-stage graph is, how to solve this. I gave you a brief idea about what is this dynamic programming as well. Okay. We will do it. Okay. We will see the remaining things in the next class.